right, now we're going to talk about the sizes of atoms and the sizes of ions. And when it comes right down to it, we like to think that atoms have very, very definite boundaries, and we know exactly how big they are. But the truth of the matter is we really don't. And it's hard to measure how big an atom actually is. And so when we look at the quantum mechanical model of the atom, what we're looking at is we're looking at an electron distribution, and there is no point of absolute no probability of finding an electron. And so there's really not a lot of direction there to tell us how big atoms are. And so we have to look to another factor or another measurement in order to figure out how big atoms really are. And so what we've decided to do is we've decided to use the distance that atoms are between one another when they bond. And so to better understand it, we need to understand the difference between a non-bonding and a bonding radii. Okay, and so what we got here, here's a graphic that hopefully will help us. Now, if you imagine that atoms are, I don't know, billiard balls smashing up against one another on a pool table, we have very, very elastic collisions when you're playing pool on a pool table. But those balls, they don't compress, they don't change, they just mash together. The energy is very elastically combined or sent back through one another. And we end up with having those electrons or those pool balls smash around pretty evenly. And if we talk about electrons that way, or atoms that way, in an interaction where they're just smashing into one another, those finite boundaries of those two atoms, they don't merge well. And they're like the pool balls where they smash off one another and they go where they need to go. However, and the reason for that is because those electron clouds can't penetrate one another, because the electrons on the very outside, if they're not bonding together, they're going to repel one another. They're going to cause those atoms not to come closely together. Okay? And so what we're looking at, that is what I'm talking about when I say this is a good demonstration of the non-bonding atomic radii. That doesn't work at all, and you can't see it. All right, we'll switch to a brighter color. Sorry about that. Okay. Non-bonding atomic radii, otherwise known as van der Waals radii. Now, if we're looking at our graphic here, that's what we see right here. So that's this distance. And I can't draw on it, or can I? No, you won't see it anyway. But that's this distance marked from here to here. This is our non-bonding radii. So if atoms are just colliding against one another, they appear to be thicker than if they bond together. And so when atoms bond together, we actually end up seeing these distances look smaller. And that's what this radius or this distance is here. Like if you were to carry this radius around, you would see that this radius probably would come down to about here, which is inside the bonding radii. And so when atoms are bonded together, we see that they are closer to one another than they otherwise would be expected. And that's going to be due to the sharing of the electrons between those atoms. Because these electrons are shared between two atoms, these two atoms have to mush a little bit closer in order to really feel each other's electrons and form a chemical bond. And so when they share, when those two atoms, sharing brings those two atoms much, much closer together than they would be expected to be otherwise. Okay, and so this is our bonding radii. Okay, and the bonding atomic radius is known to be about half the distance between the two nuclei of the bonded atom. And so that's how science defined it. They said, okay, we can establish the distance between the nuclei of these two atoms as they're bonded together. And we're going to say that the bonding radii is going to be half of that distance. And we're just assuming that it's an equal distance split. And that may not be the case all the time, but we had to make a decision, and that was the decision that was made. We're just going to kind of go with it. Now, that was how it went down. So whenever we're talking about this, the atomic size of an atom, really, that's what we're talking about, is the bonding distance. That's largely what's going to be used. Now, it is super, super, super difficult to measure the non-bonding radius of an atom. But we can measure the bonding distance of an atom pretty easily. This distance from nuclei to nuclei has been something that has been measurable for quite some time. This non-bonding atomic radii, still not something we have a pretty good handle on. And so this is the number that we use, is the bonding measurement, to make sure that we can understand what's going on. Now, the majority of the periodic table has been measured, and average values have been calculated. And so the numbers that we're going to talk about are, in fact, average values. Due to the fact that there are no compounds made with the lighter noble gases, their values are estimates. And so we have numbers here for helium and neon, but those are, and argon as well, but those are going to be estimations because we don't really have a lot of data with those being in chemical bonds. And so that's where that's at. We have some data with xenon. There was a Finnish group of researchers that did some molecules and made some molecules with xenon. But that's really the only one we got. So the rest of them are pretty much going to be estimates. Now, these are all average values. Okay, so these different numbers that you see referenced in this graphic are different values and are different averages based on hundreds of iterations of these atoms being bonded together with other atoms. And so are we always going to have exactly the same value? No. But this gives us a place to start and a place that we can come up with some data that makes sense and have a conversation about it. Okay, now in this graphic on the right, these values are given to us in angstroms. And so boron, let's see, is 0.84 angstroms is boron's bonding radius. And we go down here to neon, which is 0.56 is the estimated value. And so if you look, what we see, and this is the most important part of this, is generally speaking, the bonding radii gets smaller as we go from left to right in the periodic table. And so that's kind of what we're looking at here. Now, when we measure these things in angstroms, what I want you to know is the conversion factor for that is right here. 1 angstrom is equal to 10 to the negative 10 meters. So that is a very valuable conversion that I need you to have written down on your conversion sheet. If you don't have that done yet, make sure you do, please. And the other one that you might see a lot is you might see picometers, and that's this one right here as well. And so 1 picometer is going to be 1.0 times 10 to the negative 12 meters. So a picometer is even smaller than an angstrom. And 1 angstrom is going to equal 100.0 picometers. So if we need to talk about that conversion, that's what I want you to know. Now, as we talked about, I had mentioned that trends in the ionic radii, or atomic radii, this should be atomic, not ionic. Did I skip a? I did. Where did I go? I skipped a one. Oh, darn it. Did I lose a paragraph? Where did that paragraph go? Oh, it's right there. Haha. I moved it too far. Sorry about that. Okay. Didn't want to do that either. Okay, so trends in atomic radii. As I was just saying, when we looked at the graphic, within each group on the periodic table, the bonding radius increases as we go down a group. Okay, and that makes sense. So the bonding radius gets bigger as we go down a family in the periodic table. And that, like I said, makes a lot of sense because you're adding a bunch of protons, you're adding a bunch of electrons, you're adding a whole nother layer. And so every time I step down, I'm adding another layer, and I'm adding another layer, and I'm adding another layer. And remember, chemistry happens because of the valence electrons. Chemistry doesn't happen in the core electrons, chemistry happens in the valence level. And because chemistry happens there, that's the core electrons just kind of hang out and they're just there. Okay, so what really goes on, or what really happens, is they get a little bit bigger as we go down because we're adding a whole energy level and we're adding a whole bunch more electrons on the inside layer. Now, within the periodic table, the radius generally decreases from left to right. So if I'm over here and I'm going that way on your friend and mine, the Ultimate Party Planning Guide, the periodic table, we see a general bonding radii where it gets a little bit smaller. Now, there are exceptions to this. There's not, for every single stated rule, there's going to be some sort of an exception. And so just bear with me on that. But why is this? Well, it's because as we move that way on the periodic table, the effective nuclear charge is getting stronger. Okay, so we're adding more protons and more protons on the inside layer. We still have the same number of core electrons underneath it. And yes, we are adding valence electrons as well, but those protons on the inside start to win a little bit more, and they pull those in tighter and tighter and tighter and tighter. And so that's why we see atoms actually get a little bit smaller when we go to the right on the periodic table in a family, or in a period. Okay? Now, so that's kind of cool. Now, what do ions do? When ions chemically react, or when atoms react to become ions, they change their number of electrons. And so we want to talk about the trends within our ions as well. Okay? And so cations, which are positively charged ions, when an atom loses an electron to form a cation, a positively charged ion, the electrons are given off of the valence layer. So they're peeling off the electrons on the outside layer. Okay, so in the case of a sodium atom, you have one valence electron in that outside layer, and it peels off that one electron and gives it away. Well, now it's back into its core electron group, and so it's a little bit smaller. So cations, the electrons are given off to the valence level and the layer that is furthest away from the nucleus. So cations are smaller than the parent ions from which they form, or the parent atoms, excuse me. So cations are actually smaller because they're giving away electrons on the outside. Okay, now those electrons that are left behind, be they valence electrons or be they core electrons, are going to be more tightly held though, because you have more protons pulling on fewer electrons, and so they start to tighten them in a little bit more. So they actually get a little smaller. Okay, anions, on the other hand, which are negatively charged ions, these are when atoms are taking electrons from other atoms and they're adding them to themselves. And so we have fewer protons in the nucleus with more electrons on the outside, and those protons can't pull as hard. So anions get bigger than their parent atom that they start from. So thus anions are larger than the parent atom that makes them up. So now we have one other thing that we got to talk about in terms of these atoms and ions. And when we talk about them, we're talking about ions of having the same charge in a group or a family, and they get larger down the column. So if we're talking about the alkali metals, let's say, those ionic charges are going to get bigger for the same reason that the atoms get bigger as we go down, because we're adding more layers. And so for ions having the same charge in a same group or a family, they're going to get bigger as they go down. So here, 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 and here. So that's how that works out. Now, there's one more complication here, and that is for isoelectronic ions. So for isoelectronic ions, having the same, and these are just ions that have the same number of electrons, the story is more complicated. And in order to fully, truly appreciate and understand that story, we have to take a look at how many protons are in the nucleus. We also have to take a look at how many electrons are outside of the nucleus in the valence level and how that interaction plays out. And so let's take a peek at this graphic, and I'll show you what I mean. So I have to rewrite that for you. All right, so isoelectronic ions are those ions that have the same number of electrons. Now, what I did is I looked up some values for you. And so here we have oxygen with a 2- charge. I have fluorine with a 1- charge. I have sodium with a +1 charge, magnesium with a +2, and aluminum with a +3 charge. Okay, now, if I look at the number of protons, oxygen has got 8 protons. Okay. It's got 9. Fluorine has 9 protons. Sodium has 11. Magnesium has 12. And aluminum has 13 protons. Now, in the case of these ions, oxygen with a -2 charge means that it has 2 more electrons than it does protons. Okay, so we have 2 more electrons than we do protons that we start with. And if we look, it's fairly large. It's 1.26 is its radius in angstroms. Okay, now, fluorine has 9 protons, 10 electrons, so all of these atoms, or all of these ions, because they're isoelectronic, they're all going to have the same number of electrons. And so fluorine has 9 protons, 10 electrons, and you'll notice it's a little bit smaller. Okay, well that makes sense because there's one more proton here pulling in a little bit, and so it's one more proton that can help fight that fight and pull those electrons in just a little bit tighter. Now, here we're at sodium. Now we've gone around the corner of the periodic table. We're down now 1 energy level, but we have 11 protons, 10 electrons. They're isoelectronic, so they've still got 10 electrons. Now we have more protons than electrons pulling in, and you can see it's getting a little bit smaller still. Okay, now if we add another proton and we go to magnesium with a +2 charge, 10 electrons, look at how much different in size it gets. And we can see this even more when we get all the way over here to aluminum, where we have 13 protons and 10 electrons, and we have an ionic radius of 0.68 angstroms. All right, now, that makes sense because we've got 2 more protons here than electrons and 3 more protons than electrons here. And so really, those 13 protons are really pulling together, and they're really pulling in all those electrons as tight as they can, a lot like, I don't know, a figure skater spinning around in a circle, pulling themselves in tighter so they can spin faster. And that's really what's going on here, is these protons are pulling like mules, and they're pulling hard, and they're going to pull those electrons in tighter, and we see that manifested in the size of that ion. It's a much, 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 much smaller ion. And so whenever we're talking about ions that are isoelectronic, you actually have to kind of go through the protons and electrons to see where the numbers break and to see how things are going to look based on the number of pieces that are there. Now, most importantly here is that we can see that the radius decreases as the ion becomes more positive. That's the big picture. The more electrons that something loses, the more protons are pulling, and the more the protons are going to win. And so that's really what we're looking at here. So if we have fewer and fewer electrons on the valence level, the more and more protons in the nucleus to pull harder, the fewer electrons on the outside of the nucleus, and we see that the ionic radius gets considerably smaller with positive ions that are isoelectronic with negatively charged ions. And so that's the size of electrons and ions and how we have to work that out.